Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's our pleasure to have Nikhil Srivastava with us today. He's a postdoc at the Institute for Advanced Study, and he's one of the authors of the well-celebrated sparsification result, I hope you all know. Today he's going to talk us about restricted invertibility.
Okay, thanks.
You.
Okay, so this is an elementary proof of the restricted invertibility theorem. This is joint work with Dan Spielman. So this is about some very basic things about matrices. So suppose I have, suppose I'm given a n by m real matrix L. So this thing is, this thing is some map from Rn to R, Rm to Rn. And one of the first things I ask about a matrix is it invertible? So a matrix is invertible if x not equal to 0 implies Lx not equal to 0. And this is saying that this is some measure of degeneracy. So we think of an invertible matrix as non-degenerate or well-behaved in some weak sense. And so here's a matrix that's invertible. It's the identity matrix. And not every matrix is invertible, so you could have a matrix that looks like this, and all the columns are the same. And any matrix that has linear dependencies is not invertible. Okay. So there is one nice thing, though, which is that every matrix contains an invertible matrix, and so that is that there's a subset of the columns. There's a subset of the columns S for which there's a restriction R sub S, which is a map from Rs to, I don't know, the span of the columns of the matrix. This thing is invertible, and this is just any linearly independent set of columns. And the number of linearly independent, the maximal size of a linearly independent set of columns is called a rank. And the first thing you learn in linear algebra is that that this is a tight characterization. Every matrix has a column submatrix, size equal to the rank, which is invertible. Okay. So I can use this. So I have some kind of nasty operator like this shift operator, which just takes x1, x2, and so on, maps it, just cuts off the first one. And these things are linearly independent. I can restrict to everything except x1, and then this becomes the identity, and it's invertible. Okay. So this is roughly what I mean by restricted invertibility. You have a matrix, and you want to find a subset of the columns, which is invertible. And okay, well that's not the result. So so there is one deficiency of this nice relationship between rank and invertibility, which is that it's not very robust against noise. So if I give you, this matrix and I add some tiny amount of noise to it, it now has full rank. And yet there are vectors x for which Lx is very close to 0, and x has unit norm. So this is very close to being degenerate. Okay. And so a more robust sort of quantitative measure of degeneracy is the least singular value, sigma min, and this is the largest sigma for which Lx is bigger, norm of Lx is bigger than sigma norm of x for all vectors x. So this is a measure of how much L shrinks vectors, in the worst case. And so this thing, the least singular value is very close to 0, so this is degenerate, and the identity is sort of the most non-degenerate matrix. Its least singular value is equal to 1. Okay, and so it's not true that So I'm gonna call a matrix well invertible if sigma min is bounded away from 0 at some constant. Okay, and it's not true that every matrix has a submatrix of size a column restriction of size equal to its rank, which is well invertible. This example shows it. But let's introduce a more robust notion of rank and see if we can derive the analogous statement. So there's something called the stable rank, or the numerical rank. And the stable rank of a matrix L is the Frobenius norm squared divided by the 2 norms squared. So this is the operator norm. And this thing is, it's the sum of the eigenvalues of L transpose L divided by the largest one. Okay. And from this expression, you can see that this is always at most the rank of L. Okay, so this is some relaxation of the rank. This is not an integer. This can be any number. And this thing is, this, for example, the stable rank of this matrix is basically 1 because the Frobenius norm and the 2 norm are both basically the same. All of these vectors point in this. What are the lambda i's?
No. Yeah.
In this case? Or what are they? The eigenvalues?
No.
Yes. Oh.
One you didn't say.
Yes. The lambda i's are eigenvalues. Okay. So yeah, the singular values of L are the eigenvalues of L transpose L. Okay. Excuse me?
Singular values squared are
the singular values squared. Yes. Are the eigenvalues. Yes. Okay. So, you could try to ask the analogous question: Does this characterize the largest well-invertible column submatrix of a matrix? This question was asked by Bourgain and Tzafriri, and in 1987, they proved that the answer to this is yes, in some sense. So what they showed is, if L is an n by n matrix, so it's a square matrix with unit length columns. So they proved there are some universal constants C and D, so that for every square matrix with unit length columns, there's some subset of the columns for which the restriction L sub s, so this is just the operator you get by restricting to columns in S, as I did here. The least singular value of this is at least some constant, at least C, and the size of this thing is at least this other constant times times the stable rank. So here the Frobenius norm is just going to be n because they're unit vectors. So what this is saying is that the operator norm of this matrix is small, so if the columns don't all really point in one direction, then there must exist a subset which is well invertible. So it's sort of isomorphic to a orthogonal basis. And yeah, so they proved this. They were studying some things in functional analysis and geometry. They were studying something called the paving conjecture, and this is seen as some sigma min of this restriction L sub s.
Where does the assumption end, the conclusion start?
Oh yeah. So the assumption is unit length columns, n by n square matrix.
Yes.
And the conclusion is there exists some set which is well conditioned, or which is well invertible, and the size is so the size is some constant times the stable rank. So here the stable rank is just n divided by the operator norm squared. Okay. So yeah, so this is up to constants. This is, for example, if you give this thing an orthonormal basis, well, it'll tell you that there's something of size order n, which is well invertible, which is correct, and it will also, if you give it this thing, it'll say the best you can do is constant size matrix, which is also correct.
Why did they need it?
Why did they need this? So they're interested in. So there's something called the paving conjecture, where you're interested in partitioning a matrix into things that.
What
The paving conjecture, the Caddison-Singer conjecture.
Okay, Caddison-Singer.
Yeah.
Caddison-Singer.
So that's why they wanted this. They also used this somehow, or somebody used this to study this complemented subspace problem. I'm not that sure of the details, but I think Bill Johnson has some paper about this. But I think this was their main motivation at the time. They did this. Caddis and Singer, yeah. And okay, so originally these constants were really tiny. I think they were like 10 to the minus 72 or something like that. Now there were some improvements on this theorem. So Bourgain and Tzafriri in '91 showed that what they showed is that if I want C to be let's see. So if I want C to be epsilon, I need D to be I need D to be something like 1 minus epsilon squared, something like that. There were other constants here. There were some. Okay, so maybe there were some other constants here which were tiny, but what they said is if I wanted to get say really close to this limit C prime, I need this thing to go down quadratically. Okay, these constants were a bit better than the original ones, but essentially this is they sort of parameterized this for some parameter epsilon. So if you were more interested in getting a big set, you could set epsilon here equal to, you could set epsilon small. And if you're more interested in getting something with, just has better at least singular value, you could set epsilon to be something big. Okay. And actually, so I believe this constant. Yeah. So I believe there's actually no constant here. So you could get this thing to be as close as you want it to 1. Which is important. Okay.
Wait, what's D prime?
It's some other constant.
Oh, okay.
Yeah. So then there were some further improvements. So Verschijnen in 2001 showed this for rectangular matrices, and got C, which is the bound on the sigma min. He was able to get C squared to be something like the Frobenius norm of L squared divided by M, which is the average column length. So now the columns no longer have to be unit vectors; they can be of varying lengths, and you can get a bound on the least singular value that's a function of the average length. And then, so there are some other results. There are many papers by Casazza and his collaborators that are tweak these constants C and D for various special kinds of matrices and get better bounds for them. And then, like various special cases. And then there's a result of.
When did Casazza write about?
I think he has papers about this for many years. For the last, there are many in the 2000s. There are some in the 90s. There are. Well, Casazza also has several papers that prove things like if you could get certain strengthening of this conjecture with certain bounds, then it would imply some variant of Caddis and Singer or something like that. Then Trop in 2008 gave a randomized algorithm for getting S. So this is a randomized polynomial time algorithm. So this original proof was very non-constructive, and it was totally not clear how to get this set S. And he sort of made this proof algorithmic and got a randomized algorithm, and improved the constants. I think the order of the magnitude of these things could be improved to, say, 1/100 by this point. Okay, for certain regimes of C and D. Okay, so this is sort of what's known about this. So what we prove here is sort of like this sort of general case of Verschijnen. So what we prove is the most general known version of this theorem, which is the following. So given L n by m and epsilon greater than 0, well, less than 1, there exists subset S of size at least 1 minus epsilon squared times the stable rank. And the least singular value squared of this restriction is at least epsilon squared times the average column length. And there are no constants, and you can put whatever epsilon you want. And it's a deterministic n to the 5th time algorithm. And I mean, sort of the so first of all, this is tight. So it's quadratic dependence on epsilon, which has appeared previously in this proof. This was shown to be tight in some paper of I think Berman, Kaftal, and Weiss in the 90s. So you can't do better than this quadratic dependence on epsilon. And I don't know, if you look at the case of diagonal matrices, you can't really do better than this 1 minus epsilon thing either. So this is basically sharp, up to maybe a constant of 2. The main point of it really, though, is that it's a very simple proof, and it just uses linear algebra. It doesn't use anything. Okay. So, are there any questions about what the statement of the theorem is? Okay. So, let me sketch the proof.
Are there other applications where the average column length comes up?
Are there other applications where the average column length comes up? So I think in Verscheinen's application, he was applying this to matrices that came from John's decompositions. So this thing where you take a convex body and you look at the maximum volume ellipsoid and the contact points and have some weights. And those are all not all the same length. And so he wanted it for that. I think that's why he came up with this generalization. Okay, so let me sketch the proof. So first, let me just set some notation. So the input matrix L n by m. So I'm going to assume m is bigger than n, and I'm going to write the columns as W1 through Wm, and these are all vectors in Rn, right? And actually, I'm going to stop talking about singular values and talk about eigenvalues. So I'm going to observe that if I have some subset of the columns, then this matrix LS transpose is just equal to the sum of I and S of Wi transpose. This is just notation. Okay? And the least singular value squared of LS is actually the sth largest eigenvalue of the sum Wi transpose for I and S. Okay? So my target, which is a restriction, which is a set S so that LS has large singular value, is the same thing as a set S for which the sum of these outer products Wi transpose lying in S has the appropriate number of large eigenvalues. Okay? So from now on, I'm just going to talk about eigenvalues of sums of outer products. Okay?
So what's the case symbol you have?
Size of S. So fine. So this is like the kth eigenvalue of k is size of S. And the rest are going to be I mean if this thing is not so this k is going to be less than n, so this thing is not going to be full rank. So it's going to have some zero eigenvalues, but I'm going to be only interested in the k. Okay. So so here's like here's a plan for how this construction is going to go. Okay, so I'm going to construct this set iteratively. So my goal is to get S, and what I'm going to do is I'm going to start with nothing, and I'm going to add one vector Wi in every step. So let A be the matrix that I'm building up. Okay, so initial A is 0. After the first step, A is going to be some Wi1 transpose. So I'm going to have added one Wi, which is one column of L. And then I'm going to add one more wi1, wi1 transpose plus. Okay. Now, as I add these vectors, I'm going to keep track of a number b, which I'm going to call a barrier. So here's a picture on the real line of what's going to happen. So initially, I'm going to have my matrix A. So let this be 0. So this is a plot of the eigenvalues of A. So initially A is going to have all its eigenvalues at 0. Okay? And I'm going to keep track of this number b, which I will tell you what it is later. Now, after I add one vector to A, I'm going to have the guarantee that so when I add this, A is now going to have one positive eigenvalue, right? A is positive semi-definite. I'm going to guarantee that this thing jumps across B, okay? So I'm going to choose W, the first vector, in a way that this thing jumps across B, okay? After this, I'm going to shift B back by some fixed constant delta. So in the second step, I'm going to have B minus delta. So I now have this easier target. But then I'm going to choose wi2 so that I get another new eigenvalue, but now it lands across B minus delta, okay? And then, I'm going to have B minus 2 delta. After k steps, I'm going to have A is the sum of, k, of these outer products, right? So I'm going to, after k steps, I'm going to have, I'm fine. So I'm going to have, wi1 all the way to wik. And this thing is going to be a B minus k delta, okay? And the invariant that I'm going to maintain is that at any step, I have exactly k non-zero eigenvalues, and they're all bigger than the current barrier, okay? So at the end, what am I going to get? So this thing is going to be my set S. This is k columns, right? And if I'm able to maintain this, and I get that the kth eigenvalue of this final thing that I have is at least B minus k delta. Okay, and the way I'm going to set this up is, so the initial B is going to be roughly equal to the Frobenius norm of L divided by M. So this is, forget about M, but this is the average column length. Okay, so initially I'm going to start off with this. And the delta, the step size that I'm going to take, is going to be roughly equal to the 2 norm divided by the column length. And the number of steps I'm going to take is going to be 1 minus epsilon times the stable rank, roughly. Fine, squared, times the stable rank. Forget about the square for now. So what would happen if I actually had these numbers, right? I would start off here. At each step, I would remove the 2 norm. And I would only do this 1 minus epsilon times the ratio number of times. So at the end, B minus k delta is equal to epsilon times what B naught was, which is the average column length, right? And if I can get this, then I'm done, because this is the bound I wanted to get. If you look at the statement of that theorem, okay? I haven't put the epsilon squares. When I actually work this out, it'll be a little different. But roughly, the starting place is going to be the average column length. The step size is going to be, the 2 norm squared divided by M. And the number of steps is going to be the stable rank. Okay? Now, so of course, this whole thing, I have to prove that at every step, I can actually find a vector for which these constraints are feasible, right? So, these barrier things are constraints. So in the first step, I need to jump across here and then jump across here and so on. I need to show that there is always a sequence of vectors, columns of L, for which this thing is feasible. And that's what the proof is. But this is sort of a very bird's eye view of the proof, the construction. Yep?
There the dependence on epsilon is quadratic.
Yeah. So this is false. It'll actually get quadratic. You'll actually have some funny things going on here. Like, this is not actually what these numbers are. There's something close to this. And you'll get a quadratic dependence in the end. Okay? Okay. So Okay, so the basic operation that's going on here is at any point you have some matrix A and you have some barrier B. So initially, B is just initially it was B naught. B is just whatever the value is at the current step. Okay, and you want to add some outer product WW transpose, and you want something to happen with eigenvalues. So the basic thing so what happens when you add a rank 1 matrix to a positive semi-definite matrix? So if A had eigenvalues sitting here before, then the new eigenvalues interlace the old eigenvalues. So A had a bunch of 0 eigenvalues. When I add this WW transpose, if it has some projection outside the current span of A, then one of these guys is going to move forward. Okay? And all of these, there's going to be some new set of eigenvalues which interlace the old set of eigenvalues like this. Is everybody familiar with this fact? Okay. So my goal was, I had all these guys sitting in front of B. My goal was now to have one more eigenvalue that's bigger than B, right? So let me define, if A has k eigenvalues bigger than B, we say that some vector W is be good if A plus WW transpose has k plus 1 eigenvalues bigger than B. Okay? So I added one eigenvalue that's bigger than B. Now, so I'd like to identify when this W meets my constraint. Okay? Now there's a very simple answer to this. This is lemma 1, which is that W is B good if and only if W transpose A minus BI inverse W is less than minus 1. Okay? So this is a quadratic form in A minus BI inverse. Now, I is all matrices are over the whole n-dimensional space. So I is the identity over all n dimensions. A is not a full rank matrix. So this thing has this A minus BI has has k positive eigenvalues because A had k eigenvalues bigger than B, and it has n minus k negative eigenvalues equal to B. Okay. So let me just prove the first lemma. There are a bunch of ways to do this. Okay, so here's one really slick way, which was shown to me by Sushant Sachdeva. So let's look at the determinant of A minus BI plus WW transpose. Let's look at the inverse of the determinant. The determinant of the inverse, okay? So assuming that, so this thing is non-singular, assuming this doesn't add an eigenvalue at exactly B, this is also non-singular. This thing is equal to the determinant of A minus BI inverse times identity plus A minus BI inverse WW transpose. Wait, I'm sorry, there's no inverse here. Yeah, so this is just because determinant is a, determinant of AB is a determinant of A, determinant of B. Now, this is a rank 1 matrix. This is the identity. Determinant. This determinant is a product of eigenvalues of this matrix, right? What are the eigenvalues of this matrix? Well, you get 1, 1, 1, 1 from the identity, and you get one eigenvalue that's exactly equal to 1 plus W transpose A minus BI inverse W. Okay? Those are the eigenvalues of this thing. Okay? Okay, so this thing is equal to the product of all these numbers. Now look at what these things are, right? So recall that A had k eigenvalues bigger than B, right? So this thing is going to have k eigenvalues that are, some lambda 1 minus B up to lambda k minus B, okay? And then it's going to have a bunch of minus B eigenvalues. This is just A minus BI, okay? I'm sorry, this is just A minus BI, Okay. Now what's going to happen when I add my good vector WW transpose? One of these minus b's is going to become positive, right? So previously I had I had k eigenvalues bigger than b and n minus k eigenvalues less than b. When I add w, this guy is going to become bigger than b also, right? And so the product of eigenvalues of a minus b I divided by the product of the eigenvalues of a minus bi plus ww transpose is negative, because the parity, the number of negative eigenvalues changed, right? Okay, that means this number has to be negative, and this number is exactly that. That is exactly that equation. Okay. Yep.
What is the current size of A?
Anything. It's less than n. It's k. I mean, A is an n by n matrix. That's a sum of k outer products. Okay, so I mean, yeah. So what this is saying is that, look at A minus bi. It has some number of negative eigenvalues. If I had a good vector, that number of negative eigenvalues reduces by 1. Therefore, the product of the eigenvalues has to change sign. Therefore, this ratio, which is the determinant of this thing, has to be negative. And the determinant of this thing is literally 1 plus w transpose A minus bi inverse w. So this must be negative. And that's exactly what this is. Okay?
I'm so confused about your first line there in the decomposition. You wrote determinant inverse.
Yeah, so I guess I could have done this whole thing without the inverses, because the determinant of the inverse is...
Right, or have inverses everywhere, but the way it's written, I don't...
Okay, let me just write it again. Just maybe I added an inverse somewhere where there shouldn't have
You
been.
did it halfway without inverses.
I did it halfway without inverses? Okay, so let's just do it with... There's no reason to have inverses here, so let's just do it without inverses. A minus bi plus ww transpose. This thing is determinant of A minus bi times determinant of identity plus A minus bi inverse ww transpose, right? Now, between these things have different sign by this argument that I showed you here, right? The parity of the number of negative eigenvalues changed. Therefore, this thing is less than 0. But this thing is actually equal to 1 plus w transpose A minus bi inverse w. Okay. Yeah, thanks for... Yeah, you're right. Previously it was...
Here you wanted A has exactly k eigenvalues A
Yeah.
and B? I mean, not the way you say it, is it?
Yeah, A has exactly k eigenvalues. So assume A has some number of eigenvalues bigger than B. What are the conditions for having one more eigenvalue bigger than B? So A has exactly, yeah, fine.
Exactly.
But the point is this is one more.
It could be k plus
Yeah.
1 has.
Yeah. Okay, so is everybody okay with this? No? Okay. Okay, so that's lemma 1. So this tells me exactly which vectors are good. They have this negative quadratic form, and what does this mean intuitively? Well, it means they have large projection outside the span of A, because this A minus bi inverse, the negative part of it is just a part outside the span of A. Okay. Now, this suggests one strategy for finding good vectors. Okay. Or for showing that a good vector exists at some step, right? And that strategy is averaging. So the observation is that if the sum over all W, where W are columns of L, of W transpose A minus bi inverse W is less than minus M, where M is the number of columns, then there exists, some B good W, just by averaging. One of these has to be negative 1, right? Okay, so this motivates me to, define this potential function phi b of A, which is exactly this sum over W, W transpose A minus bi inverse W.
So you're summing at each stage all of them, not just the ones that you have.
All of them, yeah. This is actually a silly thing to do, because I know that the ones I've already added are not going to satisfy this condition. But anyway, this is a sufficient condition for existence of one good vector, right? And I can now, okay, I mean, this is some of this, quadratic forms of this matrix. I can just write this as a trace of L transpose A minus BI inverse L. Okay. So this is my potential function, and if this thing is sufficiently negative, then this observation tells me that there must exist a good vector, right? So let's take a moment to study what this function looks like. Now, yeah. So if I diagonalize, if I diagonalize this A minus BI inverse, and I get eigenvectors ui and eigenvalues lambda. I'm sorry, I just diagonalize A actually. So, and I get eigenvectors ui and eigenvalues lambda I. Then I get that this thing is equal to the sum over these I of L transpose ui transpose L divided by lambda I minus B. Okay.
A no symmetric matrix?
Excuse me. A is so A is always a sum of outer product. So A is always a symmetric matrix, and it's positive. So okay. So this expression gives sort of a more of a clear picture of what this function looks like. So suppose this is the real line, and A has some 0 eigenvalues, and there's some B, and it has some positive eigenvalues. Well, so the numerator here is just it's just a projection of my matrix L in the direction of some eigenvector, but the coefficient of that eigenvector varies as follows. So for the lambda I that are non-zero, that are bigger than B, their contribution looks something like this. There's 1 over lambda I minus B. So if these things are very close to this barrier, they have a huge positive contribution. And everybody who's negative looks like this. Okay? So the closer these are all at 0, and by the induction hypothesis, they're all, there's nobody in the middle here, but the contribution of this is, it's negative, and it gets more negative as the barrier gets closer to 0. Okay. So again, you can there are some basic facts about this function that are clear when you look at this picture. So for example, if I reduce B, if I move B towards 0, this thing only decreases because the positive contributions decrease, and these things also become more negative. Okay. This makes sense because if I move the barrier B backwards, I'm loosening the constraint for a vector to be good. It now has to jump over something that's smaller. Okay. So yeah. Okay. So this is what this picture looks like. So the problem with so I could think of having a some kind of argument where I start off with this thing pretty negative, and then I argue that it's negative, so a good vector exists, and then maybe it's still negative, so another good vector exists, and so on. The problem, nobody can see this part, presumably, right? So, okay, I should, so the problem is that the potential of A plus WW transpose is bigger than the potential A at B. And this is easily seen from this picture. What happens when I add a good vector? One of these things that used to be negative, now it becomes positive. And all these other things move forward a little bit. There's some decrease due to that, but you can prove that this really dominates. Okay? So even if I was, say, less than negative m, once I add a few vectors, I may no longer be, right? So I may be stuck. So this motivates me to, define a stronger condition on vectors. How much time do I have left? 15 minutes? 20 minutes? Okay. So this motivates me to define a stronger condition on vectors, which says that I jump across a barrier and I don't get stuck. So we'll say that W is B delta great if it's B minus delta good, and the potential at B minus delta of A plus WW transpose is at most a potential of B at A. So this incorporates this, twist that I showed you in the big picture here, where after adding a vector, I'm going to move the barrier back towards 0. And this is going to compensate for the new vector that I added, okay? So I told you that this function decreases as I move B back, right? So I'm going to move B back to B minus delta for some constant delta, okay? And I'm going to say that a vector is great if it jumps over this shifted barrier and the potential doesn't increase, okay?
If you move it back, count one of the earlier vectors and jump over B minus delta anyhow.
One of the earlier vectors?
No, not vector.
You mean these?
Yes.
These are at 0. These eigenvalues are at 0.
Oh, yeah, all 0.
They're all 0. So my induction hypothesis, recall, is that at any step you're either across a barrier or you're 0, right? Yeah.
Thank you.
So in every step you add something that jumps across, and everything else is 0.
Now they were non-zero.
Yeah. So you're weakening the constraint. You're saying now jump across something that's a bit closer, but yeah. So you'll observe that. I'll observe that if I can find a great vector, then I'm done. Because if I find a great vector, I haven't finished the argument yet, but I'm going to prove a lemma that says if I find a great vector, that a great vector exists, the potential does not increase, and some sufficient negativity of this potential is enough to ensure that a great vector exists. Then I just iterate this, okay? And that gives me this picture that you see here. So maybe I shouldn't write here because probably people can't see it. Okay, so now what I'm going to do is I'm going to prove another lemma, lemma 2, which is the analog of lemma 1 for a great vector. So I'm going to derive a condition involving quadratic forms for a vector to be great. Now how do I do this? So the lemma is the following. So if W transpose A minus B minus delta I inverse LL transpose A minus B minus delta I inverse W is at most potential of B of A times minus potential of B minus delta of A times minus 1 minus W transpose A minus B minus delta I inverse W, then it's great. Okay, so this is some large expression, but what I really want you to notice is the following. So this is a quadratic form in a positive semi-definite matrix. It's A minus B minus delta I inverse, which is not positive semi-definite, but it's that L times its transpose. This thing is positive semi-definite, so this is some positive quantity. This is a positive quantity. This is the change in potential if I just shift the barrier back. So I told you that if I shift the barrier back, the potential decreases. So the potential at B minus the potential at B minus delta is some positive number. And this minus 1 minus this quadratic form is exactly the same quadratic form you saw in the good condition, right? Except with B minus delta instead of B. So what is this equation telling you, or what is inequality telling you? It's telling you that the quadratic form, that this minus 1 minus W, minus 1 minus this quadratic form W has to be positive, has to be bigger than a certain positive number. So this is a strict strengthening of the condition for being good. Here I just had minus 1 minus this quadratic form is bigger than 0. And here I have that minus 1 minus this quadratic form is bigger than some positive number. Okay? Okay. So the derivation of this, I'll just tell you. I won't actually go through all the details. It's not hard at all. So basically, the way you do it is, you write out the new potential. So phi B minus delta of A plus WW transpose, right? This is the potential after shifting. So what is this? This is trace of L transpose A plus WW transpose minus B minus delta I inverse L. Okay? Now you use Now there's something called the Sherman-Morrison formula, where you, which gives you the formula for the inverse of a rank 1 update of a matrix. So this is just some very basic fact from linear algebra. It says that A minus A plus W transpose inverse for any invertible A is equal to A inverse minus A inverse W transpose A inverse 1 plus W transpose A inverse W. Okay? This is something that can just be derived by doing some partial Gaussian elimination or something like that. And in any case, it can be verified easily. So I'm not going to really show you the details, but clearly this speaks to this thing, which is a rank 1 update of an inverse of some quantity that we we're interested in. So I'm going to apply this to this thing, which is the new potential. And what I wanted was I want this to be at most the old potential, right? That's my condition for greatness. That's one of my conditions for greatness, that the potential does not increase, right? Now when I rearrange this, I get this. That's just what I get. I'm not going to, you just do the rearrangement, and this is what you get. And now the crucial thing is, this implies the other condition for greatness, namely that you jump across the barrier. So this is what you need for the potential not to increase, okay? But in fact, in order for the potential not to increase, you also need to jump across the barrier. There's just no way you can keep the potential small without jumping across the barrier. And this is reflected in the fact that this condition requires this thing to be positive, okay, which is a strengthening of the goodness condition that I had earlier, okay? So that's the proof of this lemma. So the lemma is if some inequality between quadratic forms of W holds, then great vector exists, P delta great vector exists, okay? So now I'm going to, so what do I really need to complete the proof? I need.
Again, the condition is for which, if this holds for all W, for some.
If this is for any W. So you need several things. So if A has, k eigenvalues, so you need A to look like in the picture. Eigenvalue is bigger than B minus delta. So this thing is.
The inequality should hold simultaneously for all W.
Yeah, for any W.
Then not that W is greater than there exists.
Oh no! I'm sorry. Then W is B delta great. This is just identifying one W. So
it's the same W. You're not requiring the inequality to hold between quadratic forms. Just for
no.
specific W, then you get that W is B delta.
Yeah. So if you give me a W and this inequality holds, then that W is B delta great. Okay. Basically that's the one I want to add. Okay. So now I'm going to again do this averaging kind of thing, which I had in that observation, to derive a condition on the potential, which implies the existence of a B delta great vector, and that is going to complete the proof, because if the potential is sufficiently negative, a good vector exists. You jump across a barrier, it's still sufficiently negative, and so on. So what is this dilemma? Well, the thing is that if the potential B of A is at most minus m minus the 2 norm of L squared divided by delta, then B delta great W exists. Okay. Now proof. I'm actually going to skip the proof completely. It's just some manipulation. It's a bit delicate, but it's you do the averaging and you do some stuff and you get this. And what I want you to take away from this is, what is this? Well, remember in the previous observation, we wanted the potential to be less than minus m. Now we want the potential to be less than minus m minus something else. Okay? So this is even more negative. Okay? And this thing depends in the right way on, for example, delta. So suppose delta is very small. It means I'm moving back very, very slowly, right? That should be harder. Well, this quantity becomes more negative as delta becomes small. Okay? So, okay, I'm not going to go into the details of this. Actually, the lemma is there's one technical condition which is also satisfied, which I won't discuss. But basically, if the potential is this negative, then a great vector exists. Okay? So now, with this lemma and the definition of greatness, if I can just iterate this and get that picture of that process that I showed you earlier. And now to finish the proof, I need to set parameters. So initially, what is the potential? So initially, A is 0, right? So I need to set B and delta, right? So what is B naught going to be? Well, initially the matrix is 0. So phi B naught is trace L transpose 0 minus B naught I inverse L. This thing, so what is this? This is just minus B times the identity inverse. So this thing is, and then you just get trace of L transpose L, which is just the Frobenius norm of L squared divided by minus B naught. Okay? This is the initial potential. Now all I need is this initial potential to be less than this number, and I'm done, because it stays small. So I want this number to be less than minus m minus this number. Okay? And now you can see that there's some interaction between this Frobenius norm and this 2 norm, and why this has something to do with the stable rank. In any case, the setting, I mean the optimal setting is the following. So you set B naught equal to, let's see, so the Frobenius norm squared over m, 1 minus epsilon. You set delta to be equal to 1 minus epsilon times the 2 norm squared divided by epsilon m. And I'm not going to go through the verification, but this thing holds with equality with these numbers. And this thing is roughly the this is basically the 2 norm. This thing is basically the Frobenius norm. And then you set k. So k, so there's a limit on what k has to be. So you can't send B behind 0 because everything totally messes up then. There's also some constraint in this technical condition, but it actually exactly matches what you would get if you just didn't want the thing to cross 0. I mean, well, the technical condition, okay, it doesn't matter. But and then you set k to be equal to epsilon squared times the stable rank. And then you get the bounds that were promised in the theorem. And am I out of time? No, I'm actually okay. So yeah, that's basically it. And this gives you an algorithm because this proves that at every step there exists a vector. There are only finitely many vectors. You just try all of them. Trying a vector involves computing a quadratic form and an inverse, which you can do in n cubed. So yeah, that's it. Thanks. Questions? Yep.
So can you say a bit about why this is optimal? I mean, certainly the proof looks hard to substantially improve, but...
So you mean why the epsilon square dependence is optimal? There's some construction involving some partial Hadamard matrices. I actually don't remember why it's optimal. I don't.
It's a wonderful result, but why would a computer scientist be interested in it?
Oh, so I'm mostly interested in this for, well, okay, so
it doesn't help with Cadiz and things like that.
Well, we were hoping for a while that it would, actually. We were trying to do that. But so why would I be interested in this? Well, okay, so I'd seen this result, this restricted invertibility around in some convex geometry papers, but more importantly, I mean, this kind of barrier function method, we use this to construct sparsifiers for graphs at some point. Now, what that result, so that's sort of like this, but it has 2 barriers, and you have to stretch the vectors by variable quantities. The main feature of this is that there's a hard constraint on adding a vector. You always have to add a vector or not add it. You can't add half a vector. Okay. So part of the motivation for us to study this was just to study the strength of this method to see if we could, basically do some construct objects so we're not allowed to scale the vectors that we're adding. So this is some method that I don't know. It's a method that you can imagine using to construct matrices, with some spectral properties. And in other applications of it that we had before, you always had to stretch or shrink the vectors. So that's part of why we paid attention to this. There's also why would other computer scientists use it? So this is related to this. So numerical analysis people do like to do this. So it's related to this rank revealing QR factorization. So in some sense, what is this extracting for you? So the numerical rank is a quantity that comes up in numerical algorithms quite a lot. And this is sort of extracting for you a set of columns that represents the numerical rank of the matrix. So the more subtle reasons for why they're interested in this, I'm not sure. But I don't know. It seemed like a pretty clean fact about matrices. So we just...
It's a fantastic result. What... Have you told Bourgain? Have you managed to tell Bourgain?
So I tried to tell Bourgain, and he said, come back later, and then I didn't. But I'll try again. So.
I thought he would say, I am no longer interested in capitalism.
Actually, so he said, I haven't thought about that in 20 years, and I'm completely obsessed with other stuff.
That's what I would expect.
So that's what he said.
I'm doing other things.
I guess so. Yeah.
So is there anything better known for matrices with spatial structure? For example, Bernoulli matrices?
So Bernoulli, I don't think there's anything better known. There are better known for like band matrices and things like that. I don't know exactly what the bounds are, but you have like so I think some better bounds are known for, I think tridiagonal matrices or like even other special classes like van der Waals matrices. You can't. You can't really hope to do better than this bound for even much better than for say even diagonal matrices. You don't have the square dependence, but
Okay, thank you again.